Good evening, everyone, once again. On the behalf of the organizing team, I welcome our expert and all the participants to the second session on third day of our faculty development program. That is Next Generation Electronics and Communication System, Empower Learning and AI. We'll start. Before we start, let me give you a very brief intro about our expert today. So, Dr. Libin Matthew is a tenured lecturer at South East Technological University, Carlow, Ireland. Prior to this, he was a teaching fellow at Trinity College, Dublin, and a scientist at A-Star, Singapore. He has obtained his PhD degree from Nanyang Technological University, Singapore, and his master's degree from NIT Kurukshetra itself. His research interests include wireless communication, signal processing, radar signal processing, brain-computer interfacing, and applied AI, among others. So he's alumnus of NIT Kurukshetra. So with this brief intro, I welcome Dr. Libin K. Matthew. So Dr.
Hi.
Libin, now it's
So
over to
I
you.
hope am I audible? So am I audible? Yeah. Am I
Yes,
audible?
yes, you are
Yeah.
audible.
So
Fine.
yeah. So let me once again let me introduce myself. I'm Libin. I'm a lecturer at Southeast Technological University, Carlow, Ireland. So so my main research expertise or research interest lies, as he mentioned, signal processing with different application areas. Once again, thank you, Professor Pankaj, for this invite so that I can give a talk in my alma mater. So because Professor Pankaj was my master's degree supervisor, so that led me to get an admission for my PhD. So where I am here, so that is a stepping stone for me. I'm very thankful. And anyway, we will, without any delay, we can move on to the presentation. So what I'll do, I'll stop my video for time, then I'll share my PPT. So let me check. Let me, is it I think
Yes, yes,
now
Libin, it's visible.
now is it in the presentation mode or?
You have not opened. Actually, your screen is shared, but not the presentation. Now we
Let me
can
check.
see three presentations: FDP on 8th October, notes and presentation. This is what is visible.
Okay. So let me check.
You just
So
open the
when
PDF or presentation.
I think, let me check. This was, I'm trying to open it now. Yeah, it's open now. So
Please share again. Actually, you have stopped sharing.
okay. I'll go back and do it. So when I start like optimize for share, then should I share Microsoft Edge tab or window or entire screen? Like
You can
maybe
share
entire
your entire
screen is
screen, not
fine.
an issue. Entire screen is fine.
Yeah. Can you see my entire screen now?
Not yet.
Not. Okay. Okay. So yeah. So good afternoon or good evening, everyone. My name is Libin, and as I mentioned, I am a lecturer at SETU Carlow. So today we will be discussing about the recent advances in basically the Doppler radar sensors for non-contact healthcare monitoring. So we will specifically focus on how the machine learning enhances these systems for critical applications like vital sign detection and also some activity recognition. So basically we will touch the main theoretical parts, theoretical foundations, how and the hardware foundations, and also mainly the machine learning aspect, and also the signal processing aspect of the stuff, like, and also the system level improvements that have occurred maybe in the primarily in the last decade. So we will structure this presentation maybe around like key maybe 6 key sessions. Like we can begin with the fundamental concept of the role of a radar hardware. Then we will that do the radar fundamentals and hardware. Then we will delve into the machine learning taxonomies and the overall integration of machine learning into the radar data pipeline. So the core of the presentation will cover the distinct roles of machine learning, which plays in enhancing vital sign measurement and enabling human activity recognition, and like AR. Then finally, then we conclude with some discussions. You can ask questions maybe, and also some challenges what I have observed, and maybe the future research directions, etc. So then, so what is the motivation behind the non-contact healthcare? So the motivation of like non-contact health sensing is deeply rooted in severe demographic shift. So the population is getting aged, like more than 65 or old is expected to nearly triple, rising from, if you take all over the world, rising from 524 million in 2010 to approximately 1.5 billion by 2050. So this rise accelerates the burden of age-related chronic diseases and increases the strain on healthcare facilities. So because we won't be able to give a facility for each and every elderly person in the hospital. So what we can do that the radar technology or the these kind of non-contact technology offers a highly valuable alternative because it provides a non-contact, non-invasive, and privacy preserving ambient intelligence suitable for continuous monitoring in daily living spaces. Because when we think, suppose not only the aged person or any person, there may be a situation comes, he needs a continuous monitoring of his vital signs, maybe not only the vital signs, maybe some movement patterns, or maybe sleeping patterns, or those items. But it is not that ideal. He put a lot of sensors in his body, and it is not that convenient. Maybe some other scenarios, like if you come across a completely burned patient, so it is not possible to put sensors on his body to get his vital signs. So with the help of this non-contact vital sign detection radar, we'll be able to monitor the vital signs and also the movement pattern in a very continuous manner. So maybe another example thing is, if you want to, let's say, find a person behind the wall, maybe it is possible with this kind of millimeter wave radar that can sorry, this vital sign detection radar can be used in maybe in many application areas, like rescue operations, like apart from these health kind of scenarios. So this dwells into the global need for non-contact healthcare. So then, if you look at the Doppler radar fundamental mechanisms, so this core of this Doppler radar operation is in the principle of detecting the frequency or a phase shift in the reflected signal. So I hope all of you know the basic operational procedure operation of the radar. So for example, by using a radar, you can find how far the object is, right? So how do you find that how far that object is? Basically, you will find the phase shift or the time delay between the transmitted signal and the reflected signal, right? So by that means you will find the round trip time So then it will say, okay, basically how much is the delay between the transmitted and the received signal, and based on the equations you will be able to find how far that the object it is allocated or it is there. But when it comes to the vital sign detection, so it will be finding the tiny movements in the chest. So there are chest movements, tiny chest movement corresponding to your breathing or heartbeats. So it will be basically, if you like, if you if you find a standstill object, how far it is, the phase shift is a DC. But when it comes to a tiny like heartbeat movements, it will be something like a, there is an like AC component associated with that phase shift. So if you look at that, the phase shift something like a x of t equal to m sine omega t, that phase shift, you can model the phase shift in a sinusoidal component. So the detection sensitivity again depends on movement amplitude with related to the wavelength. So I hope you got an idea about how a vital sign, that is a basic principle of vital sign detection. It's actually detecting the tiny movements of your hair, like chest wall. So that is a one basic, very basic concept of the fundamental mechanism of Doppler radar. So then if you look at the prominent applications, some of the key applications including monitoring sleeping infants to prevent some diseases, then performing cardiopulmonary assessments to track breathing and heart rate, maybe, and even tumor motion tracking during radiotherapy. But however, to ensure these radar measurements are accurate and clinically meaningful, maybe we need to do a validation, right? So this means comparing radar output with medically proven gold standard sensors. Maybe for instance, when measuring a breath rate, researchers compare the radar signals with data from a respiration belt or maybe an end-tidal CO2 mask. Maybe for the case of heart rate monitoring, the radar readings are validated against ECG sensor, or maybe on the right you can see in this figure, you can see different sensors are placed. You can see the examples of biomedical signal measurements such as chest and lung movement, carotid pulse or gait, maybe the, you know, the gait movements, and corresponding gold standard references like ECG, PPG, or maybe some motion sensors. So for example, if you want to find the gait movements, you can put the classical motion sensors on your leg, so that it gives exactly able to estimate the gait, so that it will act as a reference signal. So with that reference signal, you will be able to label the radar data so that you can train the system. So then uh, to quantify the performance, we use maybe statistical metrics such as mean, absolute error, maybe, and also mean error, or also maybe root mean square error. These metrics helps determine how closely the radar data matches the reference measurements. Maybe as a summary, we could say while radar technology offers a non-invasive and comfortable way to monitor health, it is reliability depends on how we carefully validate against the medical gold standard. So these, all these things comes when we make the system, or how we label the data, so that you can train better way. So I hope this is clear. Basically, what are the prominent applications that comes: sleep monitoring, burn patient monitoring, gait monitoring, maybe uh, maybe something like when it comes to a physiotherapy, you could like exercise monitoring, or this walking pattern monitoring. So you could train those kind of systems. So when it comes to the heartbeat monitoring or the respiratory rate monitoring, we could go with a combined approach like signal processing plus machine learning, like a like a hybrid approach, like classical signal processing plus machine learning. But when it comes to um, 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 movement pattern analysis, we basically rely fully on the AI systems. So what are the technological progression? So basically, while if you look at these slides, while the core concept of non-contact detection was successfully demonstrated um, before 2000, maybe in the late 90s. Current research efforts are focused on translating these proof of concepts into a practical systems. The primary engineering goals are achieving lower power consumption, lighter weight, smaller form factors, better accuracy, maybe extended detection range, and more robust operation. Maybe this technological drive is also moving systems towards practical, portable, and handheld applications, and which are facilitated by the development of integrated radar chips. Again, I want like some more other things for the progressions are how we can integrate the machine learning algorithms to improve the accuracy, because when it comes to the traditional signal processing method, there are some limitations when there is a random body movements. So the main focus of today's when it comes to the algorithm side is um, how we can reduce the random body movements with the aid of machine learning approaches. So then if you look at the overview of the radar types in healthcare, you can see mainly four types of radar. I hope all of you are familiar with these kind of radar mentioned. Those are continuous wave and FMCW radar, and stepped frequency continuous wave, that is SFCW radar, and another one is UWB infrared radar, also impulse radar. So if you look at the in healthcare system, that then the continuous wave radar is the simplest and most economical form, typically operating in 2.4 gigahertz, 5.8 gigahertz, or maybe 24 gigahertz span. It continuously transmits a single tone and is highly effective for detecting presence and very small physiological motions such as respiration and heartbeat. And the popular FMCW radar, commonly used in like 24 gigahertz or 60 gigahertz range, varies its frequency linearly over time. This allows to measure both range and velocity simultaneously, making it is a very like versatile choice for the vital sign monitoring and also the patient movement tracking. And stepped frequency continuous wave radar systems, that is SFCW radar, transmit a series of discrete frequency steps, often spanning a few hundred megahertz up to maybe several gigahertz. It enables multi-target detection and localization, and can leverage compressive sensing to enhance resolution while maintaining the fast acquisition. And the last one is like UWB impulsive radar, operates over an extremely wide bandwidth, typically from 3.1 gigahertz to 10.6 gigahertz. It provides the highest resolution and penetration capability, capable of capturing fine-grained body motion through obstacles such as clothing, maybe, or bedding. However, it tends to be more complex and expensive to implement. So overall, each radar waveform or each radar type has a particular role depending upon your required accuracy, penetration, maybe some depth, or the system complexity. So you need to choose your radar system wisely according to your application and according to your needs, so that it will give a better trade-off. And if I compare the continuous wave FMCW and UWB radar. So I would say when selecting a radar hardware for healthcare sensing, certain trade-off must be carefully considered, as I mentioned. So continuous wave radar is simple, low cost, and extremely sensitive to small physiological movements. But it does not provide the range information, and its performance degrades significantly when multiple subjects are present, limiting its use to a single person monitoring. But when it comes to the frequency modulated continuous wave radar, on the other hand, it offers high detection accuracy, range and velocity measurement, and also long distance detection. And it achieves a good balance between system complexity and performance. And it makes it versatile choice for applications such as through wall. That means you can detect a person or living object beyond a wall, so or through wall or remote biometric monitoring. Then the more advanced systems like UWB and stepped frequency continuous wave radars provide high signal to noise ratio and excellent detection accuracy. But for the case of UWB radar in particular, it delivers the highest spatial resolution and penetration capability, so making it effective in complex or cluttered environment. So one of its key strength, I could say, is the ability to suppress the interference from the reflections and multipath effects. But again, however, this advantage comes this added system complexity as it requires precise, maybe internal delay calibration. So then if you compare all these things, FMCW and SFCW radars offers a more balanced trade-off between performance and practicality, making them well suited for multi-subject vital sign detection, localization, and tracking. For my current research activities, I will use FMCW specifically from Texas Instruments. So for your information, and maybe in the future I'll be using something like maybe Wi-Fi signals for kind of joint sensing and communication. We are thinking in that direction also, how we can exploit the same signal which are used for the communication, that is Wi-Fi signal maybe, uh, to detect the presence, or you can detect the continuous measurement of vital signs when a person is sleeping or something. um, so those kind of different radar systems or different radar waveforms has different applications. But when we choose a particular radar waveform for a particular application, you need to be very wise according to get a best trade-off. I would always suggest an FMCW is the best choice for most of the applications. And if you look at the RF architecture for a homodyne quadrature radar. So it plays a crucial role in determining a radar system sensitivity, detection range, and interference rejection capabilities. So in most of the biomedical radar systems, the commonly used Doppler architecture often employs a quadrature design to overcome what's known for a null detection problem. So the null point maybe occurs when there is a local oscillator and the received signal are perfectly in phase and or exactly 180-degree out of phase. When this happens, the radar may experience a signal dropout and or produce inaccurate motion or rate measurement. So for that, actually the quadrature configuration solves this by generating two outputs, that is in phase component and the quadrature phase component. So this ensures that even if one channel approaches is a null, the other still carries the valid information. So since the vital signs such as heartbeat and respiration are very low bandwidth signal, so basically if you look at the bandwidth, maybe for the heartbeat is something like a point, maybe zero point 0.6 to 1.2, I guess. Maybe for the respiratory rate is something like a 0.3 to zero point 0.4, because you can have a 20 breathing patterns in a minute, right? So then the INQ outputs can be efficiently combined in the software using basically one of the technique called arc tangent demodulation, and this approach provides the accurate motion extraction while keeping the system cost and complexity low. So you will be having in phase component and you will be having a quadrature phase component, and using the arc tangent demodulation technique, you'll combine the information. So basically, you will be doing tan inverse of I over Q. So that's what the arc tangent demodulation does. Then if you look at the FMCW, that's what I said. I'll be using kind of FMCW for most of my research. So an FMCW radar operates by transmitting a continuous signal whose frequency is modulated, known as a chirp. So the fundamental hardware comprises a phase lock loop, that is PLL, driving a voltage controlled oscillator to execute the frequency sweep. The received echo is mixed, or we could say multiplied, with the transmitted signal, and also what it will do, once it is multiplied, it will pass through a low pass filter to get only the uh, needed areas of the signal. This inherent operation allows the like FMCW radar to measure both the distance, that is the range, and the velocity of the target. So basically the FMCW, it is the frequency changes in accordance with the time, maybe for the chirp duration, then it will again repeat. So it will be easy to find not only the tiny movements, it is also easy to find the velocity of the object. And maybe if you look at this self and mutual injection locking, so injection locking is an advanced RF front-end technique. Self injection locking uses the reflected signal from a moving target to lock the voltage controlled oscillator that the transmitted signal. So the resulting Doppler modulation in the reflected signal is carried on the VCO, that is a voltage controlled oscillation frequency or phase, from which vital signs can be extracted using two uh, self-injection locking radars that are mutually locked, which is effectively cancel random body movements noise. Maybe researchers maybe have successfully detected vital signs of object jogging on a treadmill. You can see there is a movement. You can see two radars. One is in the front side, another one is in the back side. So using that, actually with perfectly synchronized, so that it can cancel the random body movements. So some of the researchers did this kind of works, but my focus is a little bit different. So maybe another thing, you can have a compact millimeter wave design. So a practical example of modern hardware is a compact 24 gigahertz or maybe 60 gigahertz linear FMCW radar designed for the tasks like obstacle avoidance and respiration monitoring. So the prototype utilizes maybe some of, for this particular case, it's an Infineon chip including one transmitter and two INQ receive antennas. The entire unit fit into one you can see maybe 10 cross 4 cross 22 cross centimeter cube. That is a very small box, maybe weighing like less than 150 grams, so that it can easily ported, like easily implemented anywhere else. So the signal processing is handled by the algorithms programs inside a microcontroller. The system achieved maybe an experimental range resolution of around 1.2 meter, based on like 250 megahertz um, bandwidth. But there are some other advanced chips like Texas Instruments chips that has like a range of 20 meter, and those things are operating either in 24 gigahertz and 60 gigahertz, I guess. So that it has, with the Texas Instruments, we'll be able to find multiple living objects, and we can also estimate the respiratory rate and heartbeats of the multiple persons. So that, but we need to be more careful about when we designing the algorithms, so that we'll be able to get better accuracy than the traditional systems. So then if you look at the conventional signal processing pipeline, so it involves the essential processing steps like demodulation, amplification, digitalization, filtering, and ultimately the information extraction. So I hope all of you know, if you take a mm, basic communication system, you have demodulation, amplification, digitization, filtering, all those stuff. The development of signal processing algorithms aims to address basically the interference and the clutter, while moving towards practical when it comes to a portable systems. So a major constraint is achieving real-time detection, which is challenging for general purpose hardware like CPU. So for that purpose, maybe a dedicated hardware implementation sorry, such as ASIC or FPGAs are often chosen to meet the requirements of high throughput and low latency. So while using FPGA or something, we'll be able to um, customize or tailor the requirements of our algorithm so that the hardware can be tailored so that it can use all the potential. Like if you look at an FPGA, it has a lot of um, it has a lot of DSP blocks. Some look, you can create a lot of lookup tables, so it will be able to find it will be able to implement our algorithm as such, so that you can again we can optimize our signal processing flow or algorithm flow, so that you will get better accuracy and also reduced latency. And if you look at the arc tangent demodulation for robustness, so basically, as I mentioned already, it solves the null detection problem that arises when single channel Doppler radar. So the null points results in poor signals and potentially incorrect the rate of measurement. So this arc tangent demodulation compensates for DC offset by combining the I and Q channels, which I already mentioned. Then it ensures the reliable recovery of movement information. For example, the arc tangent data showed an error of only zero point 0.9 bits compared to 4.8 or 5.2 bits. So you can have a look at those kind of maybe one example. So then another thing is that clutter and motion cancellation. So I already showed an example for one method for removing the motion cancellation, but there are some other methods also proposed by the researchers by using computer vision techniques to track the movement patterns. So by using that, then using that movement pattern to reduce or to remove the signals or noise which are occurred using the movement pattern. But again, when it comes to those are the main challenges are maybe static reflections and random body motions, as I mentioned. So the random body motions corrupts both amplitude and phase of the vital sign signal. So uh, is there anyone said anything or
Oh,
yeah?
Libin, that's I think my mistake. Not an issue.
uh,
I'll mute him.
No problem, no problem. I thought somebody is
Okay.
asking something, so problem. So
No.
solutions include adaptive DC calibration, like adaptive techniques like a dual-sided detection. That's what I mentioned. Two radars can be put in one in the front, one in the back. But there are some limitations to that also. But again, that's what a mutual injection locked system demonstrated effectiveness in the random body movement cancellation. But maybe in the future, with employing what do you call um, high efficient machine learning algorithms, we can train the system so that we'll be able to reduce the reduce the interference that caused by the random body movements. So then as I mentioned about the hardware accelerations, so for applications requiring real-time processing, such as vital signs detection, FPGAs or ASICs are preferred because they meet the high throughput and low latency requirements, so that CPUs often struggle with. Then FPGAs are advantages due to their flexibility and reconfigurability, and allowing them to be used for control, digitization, filtering, demodulation, and more importantly, serving as a platform for like implementing computationally complex algorithms. Then, I could see that some of the researchers implement algorithms like compressive sensing and orthogonal matching pursuit, or maybe I think on FPGAs to enable fast parallel processing. If you look at my name in either Google Scholar or IEEE Explorer, you can see an FPGA implementation for a paper, a transaction paper on FPGA implementation for some signal processing applications. So that what I want to convey, that by using FPGA, we'll be able to mm, customize or design or optimize our signal processing application. Maybe you can come up with a like a quantized machine learning, quantized learning network or something. Maybe you may not need like full precision algorithms. Maybe out of maybe you may not need 12-bit precision. You may get the same result or almost same accuracy with 6-bit precision, so that it will be able to, you can, by employing FPGA, you can implement your machine learning algorithms in an efficient manner, so that the if you have dedicated hardware for edge processing, that will really help for low latency, to reduce the latency of the output. Then the main part is the machine learning for healthcare radar. So ML can be used at any or all steps for the radar data processing chain. So the traditional approaches limits simple filters for clutter, maybe, or it can fail for complex signals. But when it comes to machine learning, like generative AI for data augmentation, then auto encoders for complex source separation, maybe some movement removal. So maybe when we talk about the data augmentation, the reliance on methods like adding Gaussian noise is being replaced by generative AI, because usually if you want to um, generate more data, so what we do when it comes to simple communication network, we add, we have a data and we add, repeatedly use Monte Carlo simulation to add a lot of Gaussian noise, maybe, so that you will get different randomized output, right? But which are replaced by generative AI to create statistically independent samples for robust training. And during the pre-processing, where simple low-pass filters handle clutter, more complex tasks like separating vital signs from body movements utilized advanced machine learning, such as auto-encoders. Uh, Maybe deep learning also minimizes the need for handcrafted feature engineering, like as deep learning algorithms can learn data characteristics automatically, right? So then if you look at the machine learning data processing overview, you can see different approaches. I just took it from a paper. You can see the data collection and data pre-processing, and the next one is a feature extraction and the feature processing. This is very kind of like very the traditional approaches are Gaussian noise addition, geometric transformation. But when it comes to machine learning approach, you can have a generative or GAN, GPTs, etc. And if you look at the data processing, there's some loop filters, moving average filters, smoothing filters. But when it comes for that, actually, you can have, instead of those kind of applications, you can have auto encoders, um, DNN filtering. Then when it comes to feature extraction, maybe you can, in the traditional approaches like statistical features, spectral features. I won't say like we need machine learning everywhere, but we need to use machine learning when the traditional methods fails or the classical method fails. So then feature processing, like maybe some forward elimination, backward, that was used in the traditional approaches. But when it comes to machine learning based approaches, some principal component analysis, LDA, some other unsupervised approaches to do the feature processing. So then if you look at the machine learning focus areas, vital signs versus what do you call movement, or sorry, the activity recognition. The function of machine learning is differently for the two major healthcare applications. For vital signs measurement, the use of machine learning is still preliminary. It acts as an additional helping tool to increase the robustness and accuracy of established algorithms, and primarily by mitigating noise or motion artifacts. In sharp contrast, activity recognition is inherently a classification problem that is always use like or by always using the machine learning techniques. So then if you look at the machine learning taxonomies, the learning styles, I hope this one is very much familiar for everyone. The machine learning algorithms are categorized by the learning style. We can categorize in different manner. One is the learning, one of the major categorization is using their learning style. One is that is supervised learning, which is prevalent. using labeled data to map inputs to outputs, such as convolutional neural networks for biometric authentication. That is one of the example I could say give. Unsupervised learning, as you all knows, like discovers patterns in. Sorry, let me drink a mouth of water. So unsupervised learning, what it does, it like basically it finds the hidden patterns from unlabeled data, which is often used for clustering in a maybe when it comes to the um, movement patterns or denoising. Semi-supervised learning bridges a gap by utilizing limited labeled data to guide learning from larger unlabeled data sets. So currently reinforcement learning is used for automotive radar applications, but has not yet been applied to the healthcare radar up to my knowledge. So then if you look at the machine learning taxonomies in terms of network complexity, so this can also be categorized based on the complexity. As I mentioned, shallow networks involves, if you have, we can have shallow network and a deep network. So the shallow network, which involves only a single layer of non-linear feature transformation, but while suitable for simple well constrained problems, um, they struggle with generalization in complex real world scenarios. But for the case of deep neural network, utilize multiple layers for layered processing, which is analogous to the human brain. Deep learning models such as CNNs, recurring neural networks, are superior for, you can see, dealing with complex generalized radar data presentations. So then, uh, if you look at the dominant machine learning algorithms, so the convolutional neural networks, CNN, most widely utilized in algorithm for both virtual sign detection enhancement and activity recognition or activity detection, and which is optimized for processing radar data transferred into 2D image format, maybe something like time Doppler maps. And another dominant algorithm is support vector machine, which is the second most prevalent, pioneered in early um, activity recognition work. Then that is another thing is recurring neural network or long short memory, LSTMs, long short time memory, essential for handling time series and sequential movement data. So then, because when you look at this kind of, so you will get a phase information, how the phase changes in accordance the chest wall movements, right? Again, it is a time series data, so it is this recurring neural network or LSTM is very good for handling the time series and sequential movement data. So then another thing, the generative AI or GANs for data augmentation. So these generative AI, specifically generative adversarial networks, is a solution to the data scarcity issue that challenges training robust uh, deep learning models. So the GANs works by generating new data points that are statistically independent of the input data. Although the use of generative AI for vital sign measurement is still preliminary, because no, I haven't seen not much generative AI data sets which have begun to show their utility in activity recognition. But for example, studies have reported that using GAN generated data augmentation can lead to maybe like 14% increase in activity recognition accuracy. So the generative adversarial networks are yet to use in the case of vital sign detection. Maybe what we could do is the we could use synthetic data like for is vital for training deep learning models. So one method is the kinematic model, which simulates maybe micro Doppler behavior based on human joint movement data captured from other sensors, such as motion capture systems. This approach allows generation of vast amount of labeled synthetic data, which what which transfer the learning leverages this. A model trained on the like on the synthetic data is then applied as a starting point for classifying the real radar data, which overcoming the challenge of acquiring large and label data set, because the data scarcity is one of the main problems when it comes to vital sign, because it is very difficult to record the real data. So what we need to do, we need to synthetically create a good data set that is capable of um, to mimic the actual data set. So we need a more generalization. It should not be skewed or it should not be biased, so that you won't get a biased output. So then if you look at multimodal sensing and fusion, you can see, so the multimodal approaches maybe integrate different physiological signal like vital signs, gait, to improve the robustness. So the combining modalities compensates for limitations inherent in a single modality system. So fusion of radar and camera systems shows better precision in human activity recognition compared to the using either alone. Maybe it has some privacy issues, because camera captures your video, and you see computer vision algorithms, you will be able to find the gate movements. But combining this computer vision results with the radar's results, you will be able to get a better accuracy for uh, gate movements. So but look at these to example, both the sensors are non-contact, so that you will be able to, you for example, when a person is like exercising, it won't feel any discomfort, because as there is no sensors attached to his or her body, right? So the fusion of radar and camera systems shows better precision in human activity recognition compared to using either the one. So the combining range, so time and Doppler information simultaneously increases the classification accuracy. So it's like a multimodal sensing, so we need to wisely fuse the sensor information, so that we can increase the accuracy of the system with some trade-off, like maybe it increase the installation complexity or those stuff. So maybe in a month you will be able to see a PhD advertisement on this topic. You can see in whatever the things you are seeing in this page. So that okay, so then, so if you look at the evaluations on the metrics of machine learning, so one is the vital signs is mean absolute error, or mean error and mean square error. Those are very standard error mechanism to quantify the difference between radar and clinical sensors. So the statistical plots, like correlation plots, maybe Bland and Altman plots, maybe ROC curves can access the consistency and confidence range. And when it comes to the activity recognition, so it will be metrics like F1 score, precision and recall are used for multi-class classification. So there are different approaches. Maybe you can have a confusion matrix, or you can have a root mean square error for the vital sign metrics. So so that you will be able to assess the uh, accuracy and precision, or assess the what do you call performance of your algorithm and your system, basically. Then if you look at the vital sign, the challenges, the body movement mitigation. So the biggest challenge in radar vital sign monitoring is the presence of body movement, which corrupts both the amplitude and the reflection. And so the reflections are
Libin,
the reflect.
sorry to disturb
Hi,
you, but your PPT is not visible. Suddenly, it disappeared.
let me check. I
Please
think,
share it once again.
yeah, no problem. I think I accidentally.
Might be, might
Uh,
be.
um,
Yes, it's visible now.
can,
Yeah, fine, fine, fine.
okay. Fine. Yeah. Oh, I think I accidentally pressed that stop
Not an issue.
because yeah. Okay. Now it is fine. Can you see
Yeah,
that in
yeah,
presentation
yeah.
mode?
Please, right, right, right.
Yeah.
Please go. It's fine.
So yeah. So the challenge, like when what we were discussing about, yeah. So the since the moments are like so the moments the yeah, the signals, the phase information which are from not only from the movement, not only from the heartbeat, there are some interference from the movements also. So since these movements are most often non-linear, simple sources separation it is difficult to do. So the machine learning provides powerful solutions. Maybe for instance, a deep neural network can be utilized as a regression approach, trained to detect and quantify these body movements and subsequently reconstruct the respiration signal successfully. So alternatively, maybe some classification models like CNN or support vector machine can be used to detect and discard intervals affected by the body movements. So there are two approaches. One is interference cancellation, another one is distract the portions of the signal which are affected by the bodily movements. Then then the regression based approaches such as deep virtual signs are trained to predict and minimize the effects of body movements on a virtual sign measurements. This strategy significantly reduces measurement error by reconstructing the virtual sign waveform despite motion interference. So another interference method, sorry, maybe another effective method which uses autoencoders, that is often convolutional network based for source separation. So that means by using autoencoders, we'll be able to use autoencoders to learn the non-linear representations of movements, to isolate the clean vital sign signal, which demonstrating the effectiveness in reducing unwanted movements effects in basically in the radar-based measurements. So then again the accuracy improvements. So it also addresses the hardware limitations concerning like accuracy and speed. For accuracy improvement, deep learning aided systems such as a CNN model can be utilized to increase the signal to noise ratio, which is required by advanced frequency estimation techniques like and norm like Newtonized orthogonal matching pursuit. For fast signal acquisition, deep learning aided weighted schemes can quickly identify the optimal range point on the human chest, which reduces the required acquisition times to less than 1 second, minimizing lag in real-time monitoring. So maybe you can use weighted deep learning or deep learning methods. So maybe and also maybe you can use quantized deep learning for implement when it comes to implementation in FPG or something. So then if you look at the uh, different applications the unique vital signs patterns. So something what we have noticed that we have not entered into the biometric side of vital sign applications. So the unique vital sign patterns are used for security and authentication process. Maybe it can use as an additional security measure. So researchers have employed support vector machines classifier to classify um, unique classify to classify individuals based on their unique radar measurement breathing waveforms, including identity authentication for like um, maybe some OSA patients. And the CNN classifiers can segregate children based on the age group using like OTS FMCW radar. So you can see even these radar reflected radar patterns, the chest wall movement patterns can also used as a biometric applications. Then if you look at the VS vital sign signal application like health monitoring and reconstruction, so ML like enhances diagnostic capabilities using the radar data. Neural network have been proposed for basically for specific diagnostics such as dengue fever screening using radar recorded vital sign. Convolutional neural networks can also be used to reconstruct ECG signal based on the FMCW radar data, and deep learning models improve the consistency of heartbeat, heart rate variability, information derived from Doppler cardiograms. Maybe furthermore, maybe generative AI, specifically GANs, have been employed to fuse data from multiple ultra-wideband radars to detect human body orientation uh, during the virtual sign capturing time. So there are different applications in health monitoring ranging from biometric applications to the health applications. Then if you look at the current trends in the in the vital sign measurement, so the current research highly prioritize robust vital sign um, vital sign measurement under both voluntary and involuntary body movements. If you talk overall, the machine learning functions mainly as an enhancement tool, improving the accuracy and robustness of conventional vital sign detection algorithms. The algorithmic analysis shows that CNN is the dominant network, followed by support vector machine. If the goal is to measure vital signs even with movement present, maybe deep neural network based regression is deployed. Conversely, the autoencoders are used for waveform reconstruction and denoising. So then if you look at the future directions for vital sign measurement, I would say the future research should place huge importance on the early detection of cardiac and respiration anomalies. Like a major research gap exists in the use of generative AIs for vital sign measurement. We suggest, our team suggests utilizing GANs to generate synthetic heart and respiration waveforms to address the data scarcity. The novel applications could involve assessing heart mechanical movements such as calculating the point of maximal heartbeat impulse to determine the heart size. Maybe finally maybe the concept of like activity aware vital sign measurement will lead to integrate health monitoring system that provide personalized tracking. The main thing is that these are non-contact and these are non-invasive sensors. So uh, then, as I mentioned, which can be non-contact, the traditional biometric system face issues like requiring physical contact or raising privacy concern like facial recognition. But radar offers an innovative, non-intrusive solution for remote biometric identification. By capturing unique physiological data such as heart rate variability, respiration pattern, and gait characteristics, and development through world radar like systems allows these unique signatures to be acquired even through barriers, so significantly expanding use cases for security and access control. So then mentioned about true world radar capabilities, right? So the true world radar is technologically challenging due to high signal attenuation caused by the wall materials, and the noise introduced by multipath ghost reflections. So again, various systems have been implemented. The continuous wave radar has shown efficiency for human detection, even identifying like subtle micro Doppler shift from heartbeats and behind the walls, and some primarily at close range, like example 3 meters distance. FMCW radar is regarded as a versatile for like a through wall radar due to its balanced performance, successfully monitoring vital signs through walls up to 8 meters. So this, if you could implement a through wall radar detection, or if you could improve the accuracy, it will be very useful uh, for rescue applications, like when there is an earthquake happened or building is collapsed, you could use a radar to check is there any living objects are there or not. So then the UW radar provides the highest resolution and penetration capability for complex through wall radar capabilities. So then another thing is that radar and communication coexistence. So the field is moving towards a coexistence and integration of radar sensing with wireless communication. functionality to achieve compact hardware solutions. So this enables the same transceiver and antenna to serve the dual functions of sensing, that is measuring velocity or range, and communication, example transmitting collected data. The coexistence often involves sharing the same spectrum, such as the unlicensed band, like unlicensed UWB band. Then the researchers have successfully repurposed off-the-shelf Wi-Fi hardware, leveraging channel state information to capture small variations in the surroundings caused by the respiration. But most of the, unfortunately, most of the Wi-Fi routers, or they don't give the channel state information. So we may need to do something for that also. Then, as a summary, I would say ML has fundamentally transformed non-contact sensing, although its role differs between the applications. And for vital sign measurement, machine learning serves as an enhancement tool, improving the accuracy and robustness of conventional algorithms, especially in mitigating the unwanted random body movements. For activity recognition, ML is essential, with CNNs and hybrid CNN or LSTM architectures dominating classification tasks. So the deep learning models are preferred because they show consistent performance and better generalization across varied environment compared to shallow models. So the technology trends favor complex FMCW and SFCW radars for sophisticated tasks, which involves multi-subject detection and localization. So then what are the key challenges? So basically the key challenges is computational complexity and multi-subject. So the path towards practical implementation involves we need to tackling different challenges, as I mentioned. So the firstly, the computational complexity of deep learning models, which demand extensive GPU resources, limits their real-time deployment in mobile constrained environment. So there the FPGA came into the picture. So we need to like optimize the implementation of the deep learning models, maybe quantized models, or maybe tiny machine learning models. So the future research must focus on lightweight AI architectures to address this. And the second thing is multi-target detection is largely unsolved, as a reliable differentiation and tracking of multiple subjects in a cluttered environment are difficult due to the interference. So solutions involve leveraging MIMO radar systems alongside sophisticated signal processing like constant false alarm rate, like morphological filtering and clustering. So that is about the key challenges. So lastly, I want to say there are some opportunities in my lab. Maybe I'll be advertising a postdoc position for 2 years in vital sign detection in my lab. So maybe the expected start date is maybe Jan or maybe March 2026. Maybe I'll be putting the advertisement in a week time or two. So maybe there is a possibility of PhD position maybe open in a month time. So maybe when I have this, I'll put my advertisement in LinkedIn post. If any one of you are interested, you are welcome to apply. So I hope like you enjoyed this talk. So thanks for be patient for this 1 hour time. I know sometimes it is a little boring, but uh, so thanks for like yeah, thanks for watching. Maybe you can ask if you have any question. You can ask me. I'll just for the time being I'll just stop sharing. Yeah, then yeah, we can come back to the meeting. Yeah.
Yeah, Dr. Libin, thank you so much for such an informative session, and even for the postdoc and PhD position. This is really motivating for the listeners. If they are interested in the field, they can definitely prepare in the meantime and apply. So, any participants having any questions? If they are interested in the field, definitely they can apply later on, prepare
Yeah,
accordingly.
maybe you can search Libin K Matthew in LinkedIn. So I'll be putting, maybe soon I'll be putting the advertisement there. Yeah.
So I think one of the participant has asked one question in between by texting. Let me check if
I haven't seen. Let me check the
actually
messages there.
let me check. Let me check. Actually, people are concerned more about the attendance. Will the usage of this is for the earlier session. One question is any example in healthcare for choosing CW, UWB, and FMCW? I think this question
So
is
yeah, it is basically in the healthcare. Actually, my current research is more focused on the healthcare application. So is there any question? I haven't seen that question. Maybe can you reframe the question
the
again
question is
so that
like
I'll be able
any
to correctly
example
answer?
in healthcare for choosing CW, UWB, and FMCW.
Okay, and I think I may reframe the question. Maybe you can correct if who put the question. I think they're asking, is there any particular application areas those need in healthcare setting, right? An example means, for example, one scenario will explain one. Okay, I'll explain a scenario. You can imagine a completely burned patient, so you won't be able to put any sensors there, right? So you can, let's say that burn patient is lying down, and you may be able to put like a radar maybe 3 meters there, maybe on the ceiling of the wall, just above the bed. So then the burn patient is not moving, so it will be able to find, continuously monitor the vital signs. So that is one of the very good example, um, one of the potential applications, because usually if you want to put ECG sensors, you need to stick, or sometimes you may need to put some wrist watch or something. But for completely like burn patients, and again for continuous monitoring, it is not possible to do so. So I hope that answers my question. Yeah.
Actually, this question
um,
was asked by Mr.
Maybe
Hari
I'll
Kumar
I'll I'll do
Naidu.
one.
If he is listening, I don't know. Yes, yes, he is there. So I think you got your answer, Hari Kumar Naidu.
I'll put my
Yes,
LinkedIn
yes,
page.
yes,
Yeah.
yes.
Yes, yes, I replied. It's fine. Actually,
Thank you.
LinkedIn. I think this is not your LinkedIn profile. It is his Libin George
No,
Matthew.
that is not my LinkedIn.
So
That
you can
is not
put
my
there.
LinkedIn profile. What I'll do, I'll post it in. I have posted in the message, so that you can put a request on that, or you can follow me. Yeah, so that you'll be able to see when I put an advertisement.
Right, right, right. So any other questions, or if you want to interact with the presenter?
Yeah, definitely you can
Later
ask
on also
questions,
you can
or
connect with him,
not
not an
only.
issue.
Yeah, no problem. Yeah, you can. If you are interested to do any collaboration, like not only in this area, like generally in like signal processing and AI applications for wireless, and maybe if somebody is doing some research on EEG signal processing, like for brain computer applications, maybe some disease detection using EEG, like what do you call, epilepsy detection. I'm bit into that also. So yeah, you can have a look on. If you're interested for a research collaboration, I'm open to do so.
That's cool enough. Actually, yesterday also we have one expert related to this role of AI in healthcare.
Oh, okay, that's great.
So lot of AI is being used in healthcare these days.
Yeah, because it's
So I think
maybe a lot of, it's these days a lot of people are focusing on healthcare, like plus AI buzz. But some
right,
of the
right.
areas we may not need to use AI. For example, if you look at when it comes to a wireless communication, if you want to estimate channel state, there are a lot of papers in with using deep learning methods, but still when it comes to practicality, then it is difficult to implement with a, because as I mentioned, like uh, highly computationally complex algorithms, we need GPUs to solve, or you need GPU to process. So there that FPGAs comes into picture. So there are, I have collaboration with some faculty from Trinity College Dublin. So then it will be like, yeah.
Okay,
Somebody is
then
asking for session feedback link. Yeah,
actually, session feedback link will be provided after the completion of the course. There you can submit your feedback for each session. So you need not to worry. Even this, I have informed yesterday that you'll get the feedback link after the through Atal. Feedback is to be done through the Atal portal only. Okay, then thank you so
okay.
much,
Thank you.
Dr.
Thank
Libin.
you.
So,
Uh, um,
question, I am doing
somebody
MTech
is
in
asking.
AC wireless communication.
So
Yes.
basically, I also did masters from NIT Kurukshetra. I don't know whether he's from the same university or somewhere else. Anyway, whether you are from there or somewhere else, but you can focus on mainly the theory. First of all, the theoretical concept, then the implementation of, let's say, how you can implement. Maybe you can use MATLAB plus Pluto board or something to implement what you have learned, and also you can do how you can do the simulations, and yeah, you should be very well, you should brush up your signal processing, and maybe probabilistic analysis, probabilistic knowledge, and also some good programming knowledge, so that you will be able to, if you want to go for a PhD, or maybe if you want to go for industry, both will help. Yeah, thank you. Yes, thank you.
So I think there's no more question. Then we can end the session. Thank you once again, Dr. Levin, for accepting our invite.
Thank you. No problem. Thank you.
Okay, thank you. Bye
Thank
bye.
you.
Good night.
Thank you. Bye. Bye bye. Yeah.
Okay, for participants, if you are concerned about your attendance, please contact Dr. T. N. Sasamal. If you are not able to edit the sheet, or if you are facing any other problem, so you can please contact him. Your attendance will be marked. Don't worry, but please inform him.